This is going to be debugging and profiling .NET Core applications on Linux. And hopefully some of you have already looked into using .NET Core at all, or using .NET Core on Linux specifically. And if you have, you know the story is not quite what it should be. Doing .NET on Windows for ages. I've been using .NET since 2002. It's got a very large ecosystem of different performance tools, profilers, production tools. There's a lot of stuff built into Windows itself, which has .NET in mind or was tailored for .NET specifically over time. So it's a lot easier to do this sort of thing on Windows. And getting .NET ported to a different platform is not just a matter of running console write line hello world. It's also a matter of this whole ecosystem of tools, techniques, best practices for doing performance investigations, for doing debugging, for doing production work. And most of my work actually is performance investigations and production, debugging stuff for customers. I'm a consultant, so that's a large part of my work. And I've been really interested in Linux and .NET Core, this combination, and this talk is kind of a set of practices, a set of tools that work. As they tend to say, conference talks are not for really learning how to do every single thing, but more about what's possible. So if you want, there's a bunch of references for you to explore. I've also written a couple of blog posts about this with more detailed instructions. And some of this stuff keeps changing, so there's also that to bear in mind. It's all fairly new and still being changed by Microsoft and by the open source community. So my name is Sasha. I work for a training and consulting company back in Israel. It's been quite a trip here to Australia, but I've enjoyed it really much so far. My wife's also speaking at the conference, so we've turned this into a 3-week holiday, so that was pretty awesome. So again, this is a talk on debugging and profiling .NET Core apps on Linux. And again, it's worth just stopping for a moment and just sort of admiring the fact we got here, that we can actually run .NET Core apps on Linux, and we can talk about profiling them, and we can talk about advanced topics related to .NET Core on Linux. This is pretty incredible. So the 5 things I would like you to take away is profiling CPU activity, which is pretty obvious. You want to make sure you're not overloading the CPU, and if you are, what is taking my CPU time, which functions, which stack traces, which threads. We want to talk about visualizing these stack traces, for example, visualizing CPU activity using flame graphs, which are incredibly popular on Linux, less so in the Windows world, although we are getting some traction, but we'll talk about flame graphs specifically for Linux on .NET Core applications. We'll talk about some Linux tracing tools, which can be used with .NET Core processes as well, although it takes some tweaking, and we'll talk about the tweaking necessary to make it work. We'll talk about .NET Core runtime events. If you're familiar with CLR ETW events on Windows, things like garbage collection events, just-in-time compilation events, that sort of thing that you can get out of the CLR, this is also possible on Linux with, again, some tweaking, and we'll talk about LTTNG, which is the Linux equivalent for ETW that Microsoft has chosen to use. And finally, we'll also talk about generating core dumps, and again, for production use on Windows, hopefully you are familiar with core dumps or dump files, incredibly useful for any kind of post-mortem investigations in production, crashes, memory leaks, a bunch of different scenarios. So the same techniques are also applicable to Linux, and we'll talk about getting this stuff out of core dump files on Linux as well. So that's the general story. I've told you this already. A lot of this stuff changes. I've sort of tested all of these tools and scripts with .NET Core 1.1 and 2.0. But if something doesn't work, it's probably my fault, and you could definitely get in touch. A lot of this relies on scripts I kind of hacked together, so it's not exactly the recommended way of doing things. It's just sort of the only way of doing things right now, and hopefully some of these things will improve. Now, just to draw parallels between the different operating systems, this is a Linux talk, so we'll only look at the Linux side of things, but a lot of these things have equivalents on other platforms. So .NET Core obviously runs on Windows. It's a lot easier for it to run on Windows. So Windows has, for example, ETW, which is a very, very powerful instrumentation framework built into the operating system, which can be used for CPU profiling. It can be used for tracing interesting static events like garbage collections, JIT compilations, assembly loading, that sort of thing. So ETW equivalents on Linux, for example, would be perf and LTTNG, and we'll talk about both of these tools today. There's also another cool thing that you can do on Linux, but you can't do on Windows easily anyway, and that's dynamic tracing. We'll look into that as well. Just basically choosing any arbitrary function and tracing its execution without having to recompile or even launch your code again. So that's something we can do on Linux, but not so easily on Windows. We'll talk about dumps, and again, there's tools for Windows for this, and there's tools for Linux and Mac OS, and we'll analyze dump files as well. And again, there's tools for Windows, including Visual Studio, and there's slightly less user-friendly tools for this for other platforms. So there's roughly mostly equivalents for the things we want to do on all platforms. Our focus is Linux again. If you want to talk later about how to do the same things on Windows, for example, please feel free to reach me. I'll be happy to explain and show you examples. One final thing before we get started with the different tools and techniques for this presentation is the overhead. And if you're used to development time profilers, like the Visual Studio Profiler, or maybe the Intel vTune Parallel Studio, that sort of tools, the JetBrains tools like .trace and .memory, all these development time profilers usually have an overhead, which is not really acceptable for production use. And I would expect most people using .NET Core on Linux to actually do a lot of their investigations on production, because your development environment might actually be Windows with Visual Studio, but then you want to put your app in a Linux Docker container and run it there. And so a lot of the investigations we'll be doing will not be using JetBrains .trace on Windows. It will be actual work in production on Linux. And there the overhead is a lot more considerable. So a lot of profilers will just tell you up front, by running this profiler, we will slow down your app by 2,000%. And it's sort of okay for development, I guess, if it slows down your app by 2,000%. Not so much, again, for production. It's not even very good for development time if the app takes a very long time to load now, or a certain scenario takes 7 hours to go through. But that's sort of acceptable for development, not so much for production. So for a lot of tools, we'll talk briefly about overhead, and we'll even have alternatives. So this one has more overhead, that one has less overhead, but it's got a different set of requirements which might be harder for you to satisfy. So we'll talk about overhead as well. Now there's two major categories of tools that we'll be looking at, and this is not Linux specific, it's just a general observation about performance investigation tools. There's sampling tools and tracing tools. So some of you might already be familiar with the terms, just a brief overview. Sampling is for events or for things that you want to monitor, which happen at a very high frequency. So you can't possibly record or inspect every single occurrence of that thing you're monitoring. A good example of this is CPU instructions. In many cases, you want to figure out like which functions are doing a lot of CPU work in your program, but you can't record every single CPU instruction the processor is executing and then make a tally of which ones were more active. It's just going to slow you down by not 2,000%, probably to 1,000,000%. So instead, you do sampling. You look at the CPU execution in certain intervals. For example, every million clock cycles or every couple of milliseconds, and then you make a tally of which functions or which threads or which processes were active in many of those samples. So you don't record every single event, you only take samples once in a while, and then you try to draw conclusions and interpolate from these samples. Tracing, on the other hand, means you record everything. You look at every single occurrence of a certain event, and then, again, you analyze, post-process it to draw conclusions. So tracing works for lower frequency events like disk accesses or garbage collections, that sort of thing, which happens maybe tens or hundreds of times per second. Sampling works for higher frequency events, say millions of events per second. You can't no longer record every single one. So that's just a couple of techniques we'll be using. So .NET Core on Linux, what are the different tracing components, what are the different moving pieces that we can put together and get extract information from? So some of these are not really .NET Core specific. If you have a Java app running on Linux, if you have a C++ app running on Linux, there's a lot of stuff from the core operating system that you could already be using. So looking down at the bottom of this diagram, the CPU itself, and this is not even OS specific, that's also available on Windows, the CPU itself has a bunch of performance monitoring events that we could sample and record. And that helps with identifying heavy CPU consumers. It helps with stuff like cache misses, branch mispredictions, various kind of pipeline events inside the processor. So if you're optimizing your algorithms for CPU performance, the CPU itself has a bunch of performance information, and Linux makes it very easy with freely available tools to extract that information and display it. On Windows, by the way, we have the Intel tools mostly for this, and they're not really free. They're quite the opposite of free. On top of the CPU, we have the operating system kernel, which has a bunch of interesting events as well. There's two kinds of events. So one on Linux is called, a category of events is called software events. And these are like low-level OS things, such as page faults. So when you access a memory location which is not in main memory, or core migrations, when you have a thread migrating from one core to another, the scheduler moving a thread between cores. So that sort of thing can be traced on the kernel level. There's also several hundreds of static trace points in the kernel as well, in the block I/O subsystem, so stuff like writing to disk, reading from disk, networking events like a packet being received or a packet being sent. There's events in the scheduler, there's events in the interrupt processing layer, so everywhere across the Linux kernel, there's hundreds of static trace points that we could trace. And again, for our .NET apps, it might be relevant, for our Java apps as well, for Python as well, so that's not really specific for .NET Core. In user space, again, there's a set of libraries which are not .NET specific, such as the libc library, which is the C runtime, C++ runtime, the pthread library, a bunch of other libraries provided by Linux, provided by your Linux distribution, which again have some tracing data, which have some tracing events inside that we can record. And these vary across the different libraries. So libc has a lot of those, libpthread has a lot of those. Other libraries might only have a handful, but there's a lot of different things in these libraries that, again, we could be tracing. So again, drawing the parallel to Windows, that's kind of like ETW events, which you might have embedded in user space, which you might have embedded in Windows itself, in the kernel. Finally, .NET Core itself has two major components. So we have the core CLR, which is written in C++, and that has a bunch of interesting events, which are also available on Windows. It's kind of a cross-platform eventing implementation. So if you have a garbage collection started event on Linux, you also have a similar event on Windows. You also have a similar event on macOS. You just have to use different tools to record them, but the event itself, the payload, will be the same. So there's a bunch of these events which we'll look at. And the Linux tool for recording these events is called LTTNG. That's a decision Microsoft made. So they could have chosen from a variety of different tracing frameworks, and they chose to use LTTNG for a bunch of reasons. We'll look at LTTNG later. It stands for Linux Tracing Toolkit Next Generation. So it's a fairly modern library. It's a fairly modern tool set. It's pretty nice, and you can record high-frequency events using that. And finally, your .NET Core application itself can also write custom events, so kind of like log messages. You might be familiar, again, on Windows with the event source class, which is part of ETW. It writes out ETW events. So the same class is also available on Linux, and you can use it to emit tracing messages at runtime, enable them, disable them, record them, or just ignore them whenever you want. So that's kind of the different pieces of tracing that we can record. Okay. So the first thing we're going to be talking about is recording CPU samples. So taking a .NET Core application which burns a lot of CPU and trying to figure out which functions are most active, which functions are taking up lots of CPU time. And the official story for this, which I want to share with you first, and that's not what we're going to be using, is a little bash script, not so little actually, it's probably a few thousand lines of bash, called perfcollect. And so the official workflow, if you have a .NET Core app running on Linux, maybe in a container, maybe just on a bare bone VM, the official story would be the following. You download that bash script, which is just a bash script, and then you run the script with the install argument, which installs a bunch of prerequisites. And they're tailored for different distributions. So the script detects which distribution you're on, downloads the different dependencies, install them. That's all good. Then you run collection. So you run perfcollect, and that records a bunch of stuff. It basically records everything there is to record. It records CPU samples, so you can do CPU profiling. It also enables and records all the runtime events, so garbage collections, exceptions being thrown, assemblies being loaded, methods being compiled, everything is getting recorded, and that produces a zip file. Now the workflow gets a little more shady. You take that zip file and you copy it over to a Windows machine, because you can't analyze it on Linux using perfcollect. So you take the zip file and you copy it over to a Windows machine. Then you download PerfView, which is a really great tool for Windows. It's free. It's a Microsoft developed tool for analyzing performance traces, for recording ETW events, really, really useful. And then you open the trace in PerfView and you can look at the events, and you can figure out which functions are taking lots of CPU time in your .NET Core on Linux application. Now, there's several things wrong with this, and hopefully it's not going to remain the official workflow for long, but that's the story right now. Just a couple of things that come to mind. There's a very long turnaround time here. So you have to record this a recording, get a zip file, copy it over somewhere else, open it there, do analysis, maybe fix your code, go back to that machine, record the zip file again, copy it over, keep doing that. The zip files can easily grow to hundreds of megabytes for very short periods of time. So it's not something you'd be copying around like super easily, especially if it's a cloud VM somewhere and the Windows machine is in your office or that sort of setup. So that's one problem, the turnaround time. The second issue is you obviously can't do any real-time monitoring like this, right? So you have to make a zip file, copy it over, open it. You can't do real-time monitoring on the Linux box. And of course, I mean, there's no control over exactly what gets collected. So you basically say perfcollect collect, and it decides for you which events to record, goes ahead and records them. There's some tweaking you can do, but basically it records everything. So that's the official story. And we're not going to be going with the official story, because what the perfcollect script actually does is not that complicated, and we can totally replicate parts of this ourselves. So we'll be using perf. And perf is what perfcollect uses as well. Perf is a Linux tool for performance investigations. It's not .NET Core specific at all. It's just the go-to tool on Linux if you have any kind of performance investigation to do. It's part of the Linux kernel. So, I mean, it's developed as part of the Linux kernel tree. So there's always a build of perf that matches the build of the kernel you have. And if you upgrade your kernel, you also have to upgrade perf alongside. It's available, of course, for all distributions, because again, it's just part of the kernel. So for example, on Ubuntu, you'd install it from Linux Tools Common. On Red Hat, you'd install it from the perf package. So it's just out there. You have to install it. And in some cases, it might even be available out of the box. Now, perf is a command line tool with a gazillion different options. It can record, it can display, it can process events, it can do a bunch of different things. One thing we'll be doing is just recording CPU samples, but first the general architecture of what perf events look like. So the basic premise is you have different event sources. So for example, here on the left, you have some kernel events like page faults, cache misses, context switches, a bunch of different things happening. And you can also have some events in user space. For example, memory allocations in a C application. So all these events, if you enable them, go into the perf events mechanism in the kernel, which writes them out to a file or a shared memory buffer. So there's two options for you to work with. The default, which most tools use, that's also what perfcollect uses, is to go through that perf.data file. So you write out every single event occurrence to a file, and then you analyze that file a little later. You might analyze it on a Windows machine using PerfView, or you might analyze it on the same Linux box using perf itself. But you do the recording into a file, and then you analyze it later. And that's a pretty generic architecture for an event collector. The ability to work with memory buffers rather than files is pretty important, because it means you can build real-time tools. So you don't have to go through a file. You can write events to a cyclic buffer in memory and then just analyze those and discard them. So you don't have to record everything for weeks or so. So that's the general architecture. So let's see how to use this thing. I was planning to do demos, but I don't have my computer. So I do have screenshots of everything. That's sort of was my backup plan. So we're going to see how to do a perf recording and how to get reports out of it. But we do have to talk about symbolic information first. So if I were doing a demo, I'd just show you what happens if we don't take care of it first. But here I'm just going to have to fall back to the slides. So you know that on Windows as well, we need symbols, we need PDBs, right? We need PDB files to do debugging. That's the most common scenario when you encounter PDBs. But for profiling, you need PDBs as well. You need them to figure out the relationship between addresses and function names in your app, in your source code. So same thing exactly happens on Linux. You need symbolic debug information, you need debug info files in order to match addresses to function names. So for .NET code, if we did a perf recording and then we asked perf to visualize the results, we'd get a bunch of addresses, like on this slide. So all of these great numbers here, this is where our code is. This is the stuff we care about, but it's just shown as addresses. And on Windows, there's actually a fairly elaborate set of different moving pieces which work together to make sure you get symbolic information for your .NET code. On Linux, it's a little trickier, and that's part of what the perfcollect script takes care of for you. So what do you have to do to get symbolic information on Linux for the different moving pieces? So on the left, you have a call stack of a .NET app calling console write line on a Linux box. And it goes all the way from the bottom, where there's the thread initialization stuff, going through the core CLR. And then we have the green frames, which is managed code. So the main method and program.foo, which is some function. And that goes through to .NET Framework implementation, console write line, and so on, all the way down to the Linux kernel. So each of these different functions on the stack, they need symbol information. They need debug information to be resolved to function names. And the source of that debug information is different for each of those. So for example, if we're dealing with native frames, so C or C++ code on Linux, the story is pretty similar to what happens on Windows. There's debug information files which ship alongside with the binary. So you can install them separately, or you can just get them as part of the binary package itself. And these files contain all the symbolic information you're going to need to translate addresses to function names. But for managed code, the story is a little different because managed code gets compiled at runtime, right? We have the JIT compiler, which is great. So we don't have upfront information about code addresses. It all gets created when the code gets compiled at runtime. So we need a different set of information sources. And indeed, there's this weird convention on Linux that whenever you have a JIT compiled runtime, like the JVM, Node.js, .NET Core, there's this convention where the runtime would write out symbolic information for any methods that are compiled to a text file, which is stored in a certain location. By default, it's under the temp directory. So it just goes there, and then performance analysis tools can just pick it up from there and use it. So that's the convention. And Microsoft decided to go along with the same convention. So you can turn on a flag, which I'll show you in a moment, and then the .NET just-in-time compiler will write out symbolic information to that text file, which all the performance tools will be able to pick up. So here's what it looks like. Just going to skip for a moment here to show you the, these are the screenshots I was talking about. So just want to show you the switch we need to tune. So there's this, there's this com plus perf map enabled environment variable, which when turned on will instruct the CLR to write out a text file with a line for each method that gets JIT compiled. So there's going to be a line there with the method address and the method names. And perf is going to be able to pick that up. Now you have to turn this on, again, in advance. So before you launch your application, that environment variable has to be on. It does have a certain overhead because it means every method getting compiled also incurs a write to a temp file. and the file can grow pretty big as well, but it's in the temp file system, so hopefully nothing to worry about. But you definitely need to turn this on if you plan to do any debugging in production, if you plan to do performance analysis. You just have to turn this thing on in advance. I have a slide at the very end with a checklist of all the different things you need to prepare if you plan to do performance investigations in production. Okay, so assuming we have debug information, let's finally move on to getting CPU profiles, and we'll visualize those, we'll put them on the screen using flame graphs, which again is a concept a lot of Linux people are familiar with, but on Windows it's only getting traction recently. And a flame graph is a visualization method for taking a bunch of stack traces, a lot of stack traces, like millions of stack traces, and putting them in a single diagram. Now, if you used the profiler before, you've already worked with stack traces, so you might be used to various kinds of trees where you expand the tree to get through the stack trace, or maybe lists of functions or other kinds of views. Flame graphs are really, really useful, and again, even on Windows, they're getting traction now, even as part of Microsoft official tools like the Windows Performance Analyzer and that sort of thing. So what basically a flame graph does is put in a single diagram a bunch of stack traces, where each rectangle, and I'll have a bigger example to show you in a moment, each rectangle you see on the screen is a function. The vertical axis is caller-callee relationships. So if a function is on top of another function, it was called by that function. So if A is on top of B, it means that A was called by B. The horizontal axis is just alphabetic sorting, so it's not a timeline or anything, it's just alphabetically sorted. The wider something is, the more common it was, the more times that function appeared, and that's pretty much it. The colors are usually just randomly assigned to make it look pretty. That's mostly why we have different colors. It does help sort of differentiate the different functions. You could also assign colors by some other metric, like maybe C# functions would be green, and C++ functions would be yellow, and kernel functions would be orange, or whatever. There's obviously a bunch of stuff you can do. Now, the diagram itself is usually just an SVG file, and SVGs are just XML files, and XML is text, so you can do a bunch of stuff on that, like grep and zoom, and remove stuff out of it, and filter, and that sort of thing. So let's take a look at what the workflow looks like for a .NET Core app on Linux. Again, I'm sorry it's screenshots, but it's the same workflow exactly, except it's not going to be interactive. So on the left, we have set that environment variable, complas perf map enabled equals 1, and then we ran our .NET application, giving it a certain set of things to do. So it's just running there and printing dots on the console. On the right-hand side, I ran pidstat, which is a built-in tool that shows you CPU usage for a certain process, and it shows me that my CPU usage for that buggy process is pretty high. So user CPU is time spent in user space, system is time spent in kernel space, and it adds up to sometimes 100% of a CPU. So that's a CPU-intensive app. Then we run perf record. And perf record is an incantation that tells perf to sample the CPU at a certain interval and record each individual sampling into a perf.data file. Now the interval is over here at the end, -f97. That 97 means 97 times per second. So sample the CPU 97 times per second and record samples. And then you just hit Control-C to stop. And perf record says, captured and wrote that much data to perf.data, 720 samples were captured overall. You could do this for more or less, depends on your scenario. Then you use perf report, which is not actually shown on the screenshot, to get this illustration here on the right. And this is a call tree in text format. It shows you which functions called other functions. So if you start from here, the main function called the fetch function, and then the fetch function called the process result function, and so on. So you can read this thing like a tree, and it has percentage points assigned. And it's kind of like exploring in a GUI. Except if you have a lot of stack traces, if you have a real application, you might have like 5,000 screenfuls of this to go through. So you don't really want to work with the text format. It's just an illustration that you can do a lot of the stuff on the terminal, but you really want to turn this into a chart. So that's where we use perf script and pass it through a bunch of scripts that generate a flame graph. Again, all the commands are available online and the presentation as well. And that just generates at the very end an SVG file. The application, by the way, keeps running in the meantime. So we didn't have to restart it. We didn't have to stop and start it again. It's just running there. We record a few samples, and we analyze those samples on the same machine. The only thing we had to do in advance is this environment variable, because otherwise we wouldn't have function names like main and fetch and process result. We wouldn't have those. So what does the flame graph look like? This is the actual flame graph generated from this exercise. So again, remember, the wider something is, the more prominent it was, the more time we spent there. So the more prominent flame seems to be this one right in the middle. But there's also some other flames like this one here and this one here, which have a few samples. If you hover over the different rectangles, if it wasn't just a screenshot, you'd have a tooltip saying exactly the percentage points. So you don't have to just trust your eyes. Now looking on the right here, if you can see the function names, because the zoom doesn't work either, but if you look at the function names, this is a garbage collection thread. Right, the function names here, just going to read it out for you. GC heap, BGC thread stub, BGC is background GC, GC heap, GC1, GC scan, that sort of thing. This is just a thread doing garbage collection in the background. And that's okay. We recorded that, of course. This is not C# code. That's just C++ code inside the CLR. Our C# code is over here. So this is program main. And there's a bunch of functions leading up to that point in the core CLR. But this is our code here: program main, program fetch, program process result. And then we can see some of the ways it goes from here. So for example, one frame that we have a bunch of functions on is framed allocate string and then slow allocate string. So, I mean, it's not slow deliberately. It's just there's probably a fast path where you can still allocate from a local buffer, and then there's a slow path where you can't. But regardless, we have function names for our C# code, as well as for the core CLR, the Linux libraries, and so on. All the debug information is available, and we get a full fidelity flame graph. Now again, coloring could maybe help, like color the C# code yellow, green, whatever. That's definitely something you can do as a post-processing step. So that's just an illustration of getting a CPU profile of your app, where you're spending lots of CPU time, what kinds of things you're doing. There's nothing super interesting in this scenario itself. It's just really allocating a lot of stuff, and in the process it's also causing lots of garbage collections to happen in the background. So it's interesting that we have a full view of what's happening in the process, not just the C# code, everything using the CPU in that process.
That one, the slow allocate string, that is a part of .NET Core, isn't it?
I'm sorry, again?
The top one, is it part of .NET Core, or it's not our code, right?
No. So this is this here, you mean? Yeah, that's core CLR. Yeah, and this is our C# code. It's not marked meaningfully, right? It doesn't say C# or C++ next to it, but you could figure out by the function names, just if you recognize your code. Yeah. Okay, so that was CPU profiling. We do have a bunch of other scenarios to go through, so I'm gonna move ahead, and I want to talk. And I want to talk briefly about BPF, which is a different set of tools for doing performance investigations on Linux, which I want to talk to you about. In addition to perf, there are some cases where the BPF approach is going to be giving you a lower overhead and will be more suitable for continuous performance monitoring. So it's worth mentioning, even though perf is kind of the go-to tool like I just showed you. So this just illustrates the two different approaches to doing performance work on Linux. The one on top is the perf approach, which we've been going through so far, and the one on the bottom is something new. So just go through the top part first. This is what we've been doing so far. We have the perf events mechanism in the kernel, which receives events from somewhere and writes them out to a binary file, perf.data. And then you have some user space scripts, analysis processes, visualizers, whatever, generating some sort of report from that. The report could be a bunch of text. The report could be a flame graph. The report could be anything. But you go through this data file. You go through a major big file on disk. The other approach, which we'll be talking about here, is the BPF approach, where inside the kernel, there's a little analysis program that we install and run. So rather than putting all our events in a file and doing analysis after the fact in user space, we do analysis as the events arrive in the kernel using this BPF technology. Now, I wish we could spend more time talking about BPF itself. BPF stands for Berkeley Packet Filters. So it sounds like packet filtering technology. And indeed, it was used for packet filters many years ago. Started in the early 90s, was ported to Linux from BSD, so Berkeley Packet Filters. But today it can be used for performance tracing, for performance analysis, for performance investigations as well. Again, the key difference you have to remember is that with BPF, you can do aggregations, you can generate visualizations, charts, histograms, that sort of thing, right when the events arrive, and not by inspecting a huge file that has millions or billions of entries. So that's going to be the key difference. And that enables continuous performance monitoring. It enables higher frequency event collection because you don't have to store every single event to disk. There's a bunch of things opening up. And indeed, if you look at the pipe to user space, the pipe, instead of a file, becomes a data structure, which is called a map in BPF terminology. And that map is just exactly the set of data you want to pass through to user space. It's not every single event occurrence. So that's just the general story very briefly. Now, BPF itself is a kernel technology, which has a bunch of different front ends available in user space. Python, C++, Java, Go, a bunch of other languages that can interact with BPF through a set of libraries. The set of tools I'll be using is called BCC, the BPF Compiler Collection. It's an open source project that I've also contributed a couple of tools to, and there's a bunch of people working on it from Netflix, from Facebook, from PlamGrid, from VMware, a bunch of people collaborating on building new Linux performance tools that use BPF. Now, before we go there, just one minor thing you might be asking, why would we even use perf anymore, right? So if we can, instead of going through a big file, if we can just process the events in real time, why use perf at all? Why use what I've just shown you in the first 20 minutes? And the answer is BPF is fairly new. So BPF is generally available in Linux kernel 4.1 and onwards, which means roughly the last 2.5 years. Which means if you have a super old Linux distribution, like CentOS 6, for example, or Ubuntu 14, or that sort of thing that you have to keep working with, you simply don't have access to new enough kernels to use BPF. If you have Ubuntu 16, if you have CentOS 7, if you have fairly recent Linux distros which keep updating with recent kernels, you'll be able to use BPF probably today. If not, then maybe in a couple of months. But for older distributions, perf remains the tool of choice because perf has been available since Linux 2.6. It's just there. So that's roughly why we want to go into BPF. Here's a small subset of the tools we have available today built on top of BPF. There's something for everyone here. If you're doing low-level work on like file system, networking, that sort of thing, there's a bunch of tools for you. If you're working at higher levels like tracing database accesses, tracing thread events, tracing garbage collections, there's a bunch of tools for that as well. For different managed runtimes, .NET, Java, Python, a bunch of different managed runtimes out there. I'm going to show you just a couple of examples of what you can do with the BPF-based tools. Some of these things can also be done with perf, but with a higher overhead and going through a big file that you have to pay for writing and reading whenever you do a performance investigation. So just a couple of quick examples. I'm going to just probably skip this one here because it's not super interesting. I want to show the other one because we're a little short on time. So this super long invocation here on the right, which I don't expect you to memorize, basically says, I want to trace all the functions inside the core CLR which have garbage collect in their name. Now, the core CLR is open source, so I don't really have to guess function names. I can just go to the source and see what there are, but I don't remember exactly, so let's say anything that has garbage collect in its name, I want to trace. So by just running this tool, when a .NET process is active on Linux, I can get a report that says for each individual function, how many times it was invoked. So this function here was invoked once, this function here was invoked 1170 times, and so on. Now the function names look mangled, and that's just what the C++ compiler does to your functions. If you compile C++ code, it would mangle the function name slightly. There's actually a simple tool called cppfilt, which would revert this, which would give you the original C++ name back, but we didn't run this in this example. So basically, I can draw conclusions from this, even if I don't kind of like the decorated format. It looks here like a garbage collection started function and a garbage collection finished function. Both were invoked a very large number of times. It does seem like the started callback was invoked more times than the finished callback, which is curious, but we're talking about thousands of invocations anyway. So I suspect there's a lot of garbage collection going on in this process. And this is not by using the core CLR static events. It does have events for garbage collections it can emit. This is just by looking at functions, arbitrary functions inside the runtime. So that doesn't require any kind of cooperation from the application that you're tracing, and it's applicable to any language. It's applicable to JVM apps running on Linux or Python apps running on Linux or whatever, as long as you have the function name. Another example of what we could do is actually get stack traces invoking a particular function frequently, kind of like CPU profiling, but instead of profiling just arbitrary CPU work, I want to see who's calling a particular function frequently. And so I can run another tool, which is not shown here, and get a stack trace and a count at the bottom here. And that means that this stack trace was calling the function I'm interested in 3,155 times. So it's just a slightly different way of performance profiling. Rather than just looking at arbitrary CPU work, there's a certain function I'm zooming in on, and I want to know who's calling that particular function. And so that gives me, again, a managed stack as well. And so these are functions we're familiar with, like main and fetch and process result, and they are causing lots of garbage collections by doing lots of allocations, which is, again, not surprising if you recall the flame graph, but we just got there in a slightly different way. So we can use this for garbage collection tracing, for example. Now I want to show you the static events as well. And so I'm just going to jump over again. I've told you in the beginning that the equivalent for ETW events on Windows, the equivalent on Linux is called LTTNG. That's the framework Microsoft opted to use for static events coming out of .NET Core. Both the core CLR, which is the C++ part, and your .NET code, your C# code that wants to emit runtime tracing events using the event source API. So LTTNG, again, Linux Tracing Toolkit Next Generation, is fairly similar to what perf does in spirit. And by that I mean there's a kernel component which aggregates events from the kernel. There's also a user space component that aggregates events from user space, like garbage collections events, assembly load events, whatever you emit as tracing events. And these events can go to memory buffers or to files. So again, kind of like perf, kind of like any performance tracing framework out there, you can either work with memory buffers, which are limited in space, or in addition to, you could also write out to a file on disk and analyze that later. You can do real-time processing, or you can look at the whole file after the fact with a bunch of different tracing tools. One advantage this architecture has compared to perf is that the file format is actually standardized. So it's not the random binary perf format, it's CTF, which is the common trace format. And there's a bunch of different tools from a variety of vendors that can write and read CTF files. It's kind of a common log binary format, which a lot of tools would recognize. So .NET Core itself, again, has a bunch of different events it can write out through LTTNG. So I want to show you again a demo of some of those. So the general process is as follows. For the .NET process to emit events, you need to enable yet another environment variable, which is called com+ enable event log. If you don't, there's not going to be any events. It's just quite as simple as that. You can't enable just a subset of events. You either turn the whole thing on or the whole thing off, and then the CLR will emit or not emit any events. You run your application, and in the background, you can do whenever you want, you can create a recording of these events getting emitted. So there's a bunch of commands you have to run for this, which again, no one is supposed to memorize. You can obviously script it out. So LTTNG create a trace, add context, enable certain events you're interested in, start the recording, stop the recording, destroy the session, and then you have a file on disk you can analyze later. Now the file again is in binary format, but you can inspect it with a bunch of different tools. The one built in that just comes with LTTNG if you install it from your package distribution is called Babel trace. So it reads an arbitrary common trace format file and just prints out a text listing of all the events in that file. So you can just see it's a fairly simple format. You can just see individual events. Now these aren't super interesting, but let's take a look at slightly more interesting events. So here I've just used grep to look for exception thrown events. And now you can see a bunch of lines here, each indicating an exception that was thrown in that trace recording. So they're all pretty much the same. .NET runtime exception thrown. It gives me the process name, the exception type, which was HTTP request exception, the exception message I got, and a bunch of other stuff. One notable thing missing is the call stack. There's no call stack, right? And when you have an exception event, the call stack might be kind of important and interesting. Unfortunately, probably the only drawback that LTTNG has right now is it doesn't support stack trace collection. So whenever you have an event, you get a lot of stuff in there, like the process name, process ID, timestamp, and so on. You can't get the call stack embedded inside the event automatically. And this is something a lot of other tracing frameworks actually do support, but that was a conscious decision Microsoft made, the core CLR team made. They opted to use LTTNG knowing that they won't get stack trace support. The LTTNG team is working on adding stack trace support at some future maybe release. It's an open source project. You can also contribute. But right now, you can't do meaningful stack trace collection for core CLR events. So for GC events, for exception events, for assembly load events, you can get the event information, but not the call stack. On Windows, you can. On Windows ETW supports stack trace collection for ages. It's just not something available on Linux. And it's really painful. I'm only mentioning this as a drawback because it is a pretty painful drawback. So a couple of other things you can do with these trace files, and these are just examples. There's obviously a lot more. So this one here is a plot that a guy called Alexei Vereshchagin has created from the GC events. This gives you a plot of your .NET memory usage over time. So it just looks at the garbage collection events in that trace and draws a plot of time and amount of memory in your .NET heaps. Now, if you've ever done this sort of thing on Windows it's like super trivial to do this with performance counters. It takes 5 seconds to get this kind of graph. On Linux, unfortunately, the CLR doesn't have performance counters, and there's no such thing as performance counters on Linux. So the next best thing is getting out those GC events and analyzing them in real time to produce a plot. So that's certainly doable, but someone else has to do it. This example over here is just a bunch of shell pipes that look at all the allocation events in the runtime and give you statistics over which types were allocated more frequently. So again, just another kind of thing that you can do. So 39 allocations of system byte array, 20 allocations of system string, and so on. These are sampled allocations, so it's not every single allocation that gets recorded. That would be way too expensive. It's just every 100 kilobytes you get an allocation event for that sample. So that's just a couple of examples of what you can do by analyzing those recordings of the CLR events that I wanted to show you. So the final thing I want to discuss with you, and it's going to probably take a little more than 4 minutes, but I hope to finish on time. So the very last thing I wanted to talk to you briefly about is core dump analysis. And again, I wanted to show you a nice demo, but I do have screenshots covering the whole thing. So hopefully core dumps, again, you're familiar with. A core dump is a snapshot of a process, of a running process. On Windows, they're usually not called core dumps. They're usually just called dumps or mini dumps or dump files. On Linux, it's core dumps, but it's pretty much the same thing. You take the process, you suspend it for a moment, you write out the whole thing to a file, and you let the process keep running. And this can be useful for crash analysis. If you have a process just crashing under you, you can record its state at the moment of the crash and then let it crash, and you can analyze the crash later. Or it can be useful for just live analysis, memory leaks accumulating over time, or maybe you have a deadlock and your process is stuck and you want to figure out what's happening. So that's where core dumps can be useful. Now remember, again, we're dealing with a slightly more production angle than development. So you usually can't attach a debugger in production. You don't usually even have the debugger installed in production. And core dumps are kind of the next best thing. So how to generate core dumps? This is, again, not really .NET specific. Linux has a bunch of knobs that you have to tune to make sure you get core dumps on crashes, for example. There's a file, which is in procfs, so it's not a real file. It's a system setting that you can tune to modify where the core file goes, where the dump gets written, and if it gets written in the first place. And there's also a limit that you can set per session that controls the core file size. And in some environments, it might be set to 0 by default. So the maximum size of the dump is 0 bytes, which means you won't ever get core dumps. So you do have to tweak those. If you do, if you just tweak those two, you will get crash dumps, you will get core dumps on crashes. If you want a core dump on demand, there's again a bunch of tools that you can use. The easiest one being just gcore, which is part of the GDB debugger. Gcore just takes a process, attaches to it, writes out a dump file, and detaches. It's just giving you a dump file on demand. Now, what do you do with the .NET dump file? So the only debugger currently capable of opening .NET Core dump files on Linux is lldb. You can't take that core file and open it in Visual Studio. You can't take that core file and open it in GDB. The only debugger that works is lldb. And you need a specific version of lldb which matches the version of the core CLR that you happen to be using. Currently, it's lldb 3.6, even though lldb 3.9 is now available, but you do have to stick to 3.6. So you open the dump file in lldb, and you get a prompt. It's a text-based debugger, so forget Visual Studio and nice tool windows. And then you run the bt command, which stands for backtrace. That's supposed to give you a stack trace of where you crashed, for example. Here's where you crashed. These are the frames you care about. These are the managed functions which cause the exceptions. If you look at the bottom and the top of the stack, there's function names here, but these are unmanaged C++ functions in core CLR. But the managed frames, the C# frames, gone. Now, again, you might expect a map file, like with the perf approach. A map file would be somewhere, and then you just feed that map file to the debugger. No, lldb doesn't use the same approach. You don't need a map file. What you need is a plugin which Microsoft provides. It builds alongside core CLR itself, and that plugin is called libsosplugin. Now, if you used WinDBG on Windows, you know there is SOS on Windows, which is a plugin, which is an extension for WinDBG that you can use to do managed analysis in WinDBG. Same thing here. It's the same source code, so Microsoft just ported the plugin to Linux, and it's now called libsosplugin.so. You load that into lldb, and then you get a bunch of commands, like show me the .NET stack, show me my objects on the heap, show me the contents of a particular object or array. So you get a bunch of text commands for analyzing the state of your process. So just to walk you through a couple of screenshots just very quickly here, we ran a .NET process and it crashed, and that's what it printed to the console. So unhandled exception, system application exception, task crashed. And the call stack, it doesn't look meaningful. It says here, task exception holder finalize, task scheduler publish and observe task exception, and then handle unhandled exceptions. So you don't really know where the original exception came from. You might have run into something like this with your own code if you have tasks throwing unhandled exceptions. But it says here, core dumped. Good, so we have a core file to analyze. Now, opening that core file in lldb 3.6 here on the right just prints out a bunch of stuff, which is totally unimportant. Just ignore this whole thing. It shows you the state of each single thread. But then if you run bt, it shows you the stack we saw on one of the screenshots, the one that has a bunch of missing frames. Okay, so we go ahead and load the SOS plugin, and then we can finally use a command called print exception, which prints the exception information and the call stack. But this is still the same bad call stack. It's still the same call stack we saw in the terminal, which has task exception holder finalize and publish unobserved task exception. But what's nice is that if we actually look at the thread call stack, the publish unobserved task exception function and the handle unhandled exceptions function, it takes an event args which has the original exception inside. So it's not super interesting. I'm just gonna skip through it real quick. You can look at the stack, you can extract the object out of there, you can look into the object, you can find the original exception, like you would in Visual Studio in about 3.5 seconds, but here it would take a bunch of spelunking through text-based commands. So we look at the stack and we look at the event args parameter, which is over here, and then we ask to print out that object, and that object has an exception property at this address, and then we print that, and that's an aggregate exception object, and it has a list of inner exceptions here on the bottom at this address, and then we grab that and we print it out, and it's a read-only collection, and the read-only collection has an array inside called list at this address, and we print that out, and that's an array of exceptions, and the only element in that array is at this address, and then we print the exception, and here it is. So it was an invalid operation exception, which happened at this call stack. Okay, and that's what we were after. So the original exception that caused the whole sequence of events to unfold. So somewhere in program update async, I had an exception thrown. So again, just an example of why you'd actually go through all these commands, because the terminal output doesn't show you what you're after. So that's, again, some of the things you might have learned about using WinDBG and SOS on Windows would certainly apply here as well. And again, currently you can't grab the core file and just open it in Visual Studio like you're used to on Windows. So for now, this is the workflow we're stuck with. So here's a quick checklist that you'll be able to take a look at later for what you need to do to prepare your production environment. So it has all the different things like the perf map enabled variable and the event log variable and the setup you need to do, installations, and so on. This is things you need to do in your production environment, so you'll be able to replicate some of my examples. So I hoped to show you in this really quick tour how to profile CPU activity in .NET Core applications and how to visualize them using flame graphs. We saw a couple of Linux tracing tools that you could use with .NET Core, like perf and the BCC tools. We talked about .NET Core runtime events, like garbage collections, exceptions getting thrown, and how LTTNG can collect them. And we took a quick look at generating and opening core dumps as well. It's all super painful right now, and it's all just hacked together from different bits and pieces. I've blogged about this. There's a bunch of references you can take a look at here. The slides are over there, and there's also a bunch of labs for Linux tracing if you're interested in this. I have a bunch of labs on Java and Node and .NET as well available on GitHub for you to take a look. If you have any questions, we have a long 1-hour break now, so please feel free to stay here and just ask whatever you'd like. And if you want to go, please go ahead. Thank you very much for coming. I hope you enjoyed the rest of NDC, and sorry about all the trouble.